Hello students, welcome to the class. So in the previous class, we have discussed about the Thomson's model, the drawbacks of Thomson's model, why it was not successful. And we have discussed Rutherford's model, all the achievements of Rutherford through his experiment gold foil. And but still with so those achievements also it was not successful with some drawbacks. That all we have discussed. Yeah. Moving to the next concept in this topic, that is atomic number. So what do we mean by atomic number? Atomic number, we usually use lot many times the atomic numbers of the elements, right? Atomic number is denoted by the symbol Z. Yes. Okay. So atomic number is what? The number of protons present in the nucleus is nothing but atomic number. For example, the number of protons in hydrogen nucleus is 1. In sodium atom it is 11. Therefore, their atomic numbers are 1 and 11 respectively. Okay. In order to keep the electrical neutrality, the number of electrons in an atom is equal to number of protons. That is atomic number. For example, number of electrons in hydrogen and sodium are 1 and 11 respectively. So I can define atomic number Z as number of protons in the nucleus of an atom or number of electrons in the neutral atom. Here is my point of concern. So what do we mean by neutral atom? See, when we speak about atomic number, usually students give the definition like atomic number is number of protons in the nucleus of an atom. In the nucleus of an atom, right? Okay. And we know that protons are present in the nucleus. Or it is also defined as number of electrons in electrically neutral atom. Electrically neutral atom. Now the question arises, atom is electrically neutral, right? What does that mean? The number of protons is equal to number of electrons, right? And that should be equal to atomic number. Let me take an example of two atoms. Let me consider the example here of this atom, and even I'll consider one more example of this atom. So let me say what are the atoms I've taken. Here I have taken sodium atom and here I have taken fluorine atom. Okay. Now sodium, I say in the nucleus of sodium atom, there are 11 protons. So sodium atom has 11 protons. How many electrons will be there? Quite obvious, there will be 11 electrons. So what is the atomic number of sodium? It is 11. Z denotes the atomic number because it has got 11 protons, or you can say it has got 11 electrons. Similarly, fluorine, in the nucleus of fluorine atom, you can see the difference what I have made. Atomic size of this sodium is big and this fluorine is small. In the nucleus of fluorine atom, there are 9 protons. So fluorine atom has 9 protons. That means it will have 9 electrons. So atomic number of fluorine is 9. Correct. So this is electrically neutral atom where number of protons and number of electrons are same. What if my sodium atom is a metallic atom. Metals are electropositive. They tend to lose electrons. If sodium loses one electron, if sodium loses one electron, so sodium is there, it is going to lose one electron. When it loses one electron, what happens? Let us see. Sodium neutral atom, let me say, it has got 11 protons, it has got 11 electrons. When sodium loses one electron, number of electrons become 10 and number of protons still remain 11. So remember, when it loses one electron, number of electrons become 10. Protons become 11. So which number is more? Proton number is more. Protons are what? Positively charged. So it will get plus sign. By how much number proton number is more? By one number. So it becomes Na plus ion. And this ion we call it as a cation, right? So always metals tend to lose electrons. Metals tend to lose electrons and form cations. Okay. Fluorine atom, if you take, fluorine atom is a non-metallic atom. It gains electrons. Let me say fluorine gains 1 electron. So fluorine will gain 1 electron. So fluorine has got 9 protons. It has got 9 electrons. When it gains 1 electron, number of protons still remain the same, but number of electrons become 10. Understanding? So which number is more? Electron number is more. Electron is negatively charged, minus. By how much number? By one number it is more. So it is this ion formed, and this ion is called anion. Understanding? So when you consider a cation or an anion, when you are considering a cation, yes, or you are considering an anion, the number of protons and number of electrons are not same. The number of protons and number of electrons are not same. Only when the atom is neutral, number of protons and number of electrons are same. That's the reason we define atomic number as number of protons in the nucleus of an atom, and or a number of electrons in the electrically neutral atom. Only when the atom is electrically neutral, the number of protons and number of electrons will be same. But if the atom is in the form of ion, then we cannot say atomic number is equal to proton number or electron number. We become wrong here. That time we are going to say only atomic number is equal to number of protons. Understood? So always metals form cations, non-metals form anions. Please do remember it. Cations are positively charged ions formed by loss of one or more electrons. Anions are negatively charged ions formed by gain of one or more electrons. Understanding? So atomic number is number of protons in the nucleus of an atom, or number of electrons in the electrically neutral atom. Only when the atom is electrically neutral, number of protons is equal to number of electrons. So this is about the atomic number. Fine. And it is denoted by symbol Z. So we say number of electrons in the neutral atom. Coming to the mass number. Mass number is denoted by the symbol capital A. So what is mass number? So mass number is number of protons and neutrons present in the nucleus of an atom. So we know that into the nucleus of an atom, yeah. So let me say this is my atom. And let me say this is nucleus. Okay. So what is present in the nucleus? There are protons and neutrons, and electrons are revolving around the nucleus. According to Rutherford's theory, we know only till here now. So what is mass number? Mass number is the total number of protons and neutrons which are present in the nucleus. Since protons and neutrons are present in the nucleus, they are also called nucleons. They are collectively called, not also, they are collectively called as nucleons. What are nucleons? Protons and neutrons together. Collectively, they are called as nucleons. Why they are called so? Because they are present in the nucleus. And that is what? That is nothing but mass number. Mass number denoted as A. Or sometimes we call it as atomic mass number also. You need not get confused. Atomic mass number. So mass number is what? The total number of protons and neutrons present in the nucleus are collectively known as nucleons. The total number of nucleons is termed as mass number. So using this definition, can I say mass number is equal to number of protons plus number of neutrons? Yes. So I will say mass number A is equal to number of protons plus number of neutrons, because this is nucleons. That is nothing but mass number. Now tell me, what is number of protons? Number of protons is nothing but Z, atomic number, plus number of neutrons. So using this formula, you can find, if mass number and atomic number is given, you can find the number of neutrons. And number of neutrons will be equal to A minus Z. What is A? Mass number. And Z is what? Is the atomic number. Or you can say number of protons. So if you are supposed to find number of neutrons, you can use this formula. Or if you want to find mass number, you can use this formula or this formula. Any of them can be used. If they have given protons, you will use this formula. If they have given atomic number, you will use this formula. One at the same. So this is atomic number and mass number and how they are interrelated to each other. Right? Okay. So number of neutrons can be found out. So here, this is the, I have given short, around 20 elements I have taken. the element name, the atomic number, and the mass number I have considered. So hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, first 10 elements. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium. The next 10 members. So we have around 20 members here. So the atomic numbers of these and the atomic masses. See, when we say atomic masses, they are all whole numbers except chlorine. Chlorine comes in a decimal point. Okay. So this is how we give the mass number and speak about the mass number and the atomic number. Now, when you know mass number and atomic number, how do we represent an element? We know that atomic number is represented as this capital Z, and mass number is represented as capital A. Suppose I take element, any element, I will represent it as X. Then what is the representation of an element? Indicating mass number and atomic number. What we do is, we represent it like this. Z, X and A. Z is written as suffix, A is written as, Z is written as subscript, A is written as superscript, and X is the symbol of the element. So how do we write it? Z stands for atomic number, A stands for mass number, and X is the symbol of the element. For example, if I say sodium, its atomic number is 11, its mass number is 23. So how do we represent it? We write the symbol of the element. Atomic number is written here, mass number is written here. So using this, can you calculate number of neutrons? Number of neutrons, either write it as small n or capital N, it is A minus Z. So 23 minus 11. How much you get? 23 minus 11. So it is 12. Correct? So this is how we find the number of neutrons. Okay, fine. So here we have the mass, atomic masses and atomic numbers. Using these concepts, we'll try to understand certain other things now. Isotopes. What are isotopes? Atoms with identical atomic number but different atomic mass number are known as isotopes. Or you can define it like this also. When atomic number is identical, atomic number is same, that means atoms with same atomic number, that means they belong to same element, right? Yes, so I can say atoms of same element also. Atoms of same element with same atomic number but different mass number. Yes, same atomic number but different mass number. And what are the characteristics of these isotopes? Since the isotope of an element have same atomic number but the different mass number is differing. Why the mass number will differ? Atomic number means protons and protons are equal to electrons, correct? So mass number is differing means what? It will have different number of neutrons. Isotopes differ in number of neutrons. Isotopes differ in number of neutrons. Please do remember this. They differ in number of neutrons. Since the isotopes differ in their atomic masses, all the properties of isotopes depending upon the mass, they are different. Yes, depending upon the mass, whatever properties come, they will be different. Since the chemical properties are mainly determined by the number of protons in the nucleus and number of electrons in the atom, the different isotopes of the element exhibit similar chemical properties. For example, all the isotopes of carbon on burning give carbon dioxide only. So chemical properties do not change. Yes. So let us take some of the examples of isotopes. Here is the first and the very important useful example of isotope of the element, that is isotopes of hydrogen. So these are the isotopes of hydrogen. And I have mentioned it very clearly. There are three isotopes of hydrogen: protium, deuterium, tritium. Protium is written like this, 1H1. So this one represents what? Atomic number. This one represents mass number. Deuterium is written as 1H2, or sometimes it is written as 1D2. And tritium is written as 1H3, Sometimes it is written as 1T3. So this is atomic number and this is mass number. So mass number is for protium is 1, deuterium is 2 and tritium is 3. How many protons? It is 1 only because atomic number is same. So how many neutrons? Here A minus Z, there is 0. Protium has no neutrons. Please do remember this. Protium has no neutrons. Deuterium 2 minus 1 has 1 neutron. Tritium 3 minus 1 has got 2 neutrons. So you can see here in protium there is 1 proton and 1 electron only. In deuterium 1 proton, 1 electron and 1 neutron. In tritium 1 proton, 1 electron and 2 neutrons. Is that clear? So 2 neutrons. So this is example for isotopes of hydrogen. Next, isotopes of chlorine. There are 2 isotopes of chlorine with mass number 35 and 37. You can see here 17Cl35, 17Cl37. Atomic numbers are same, mass numbers are different. So mass numbers for this is 35 and here it is 37. How many number of protons? 35 minus 17 comes to 18. 37 minus 17 comes to 20. So number of neutrons differ for isotopes. The 2 isotopes differ in their number of neutrons. Here it is 18 and 20 respectively. Isotopes of some common elements. Just now I said carbon, chemical reactivity will be same, 6C12, 6C13 and 6C14. Here what we need to know is this isotope of carbon is radioactive and it is used in carbon dating. Not going date with carbon. It is used in carbon dating means to find the age of the fossils. It is being used. Yes. Okay. Then nitrogen has got 2 isotopes 7N14 and 7N15. 7N15 is radioactive. Oxygen 8O16, 8O17, 8O18. Atomic number is same, mass number is different. Chlorine 2 isotopes. Uranium has got 3 isotopes 92U235, 92U238, 92U239. Sulfur has got 4 isotopes. So these are the common examples of the isotopes of the elements. Understanding? Yes. So this is about the isotopes of, you can find for all the examples what I have mentioned here, you can find the number of neutrons. You will get the answer. Number of neutrons differ. Coming to the next one. Isobars. What are isobars? They are atoms of different elements. When we say different elements, what is different? When we say they are atoms of different elements, Z is different, correct? Because only when elements are different, atomic number differs. Then what is same? They have same number of nucleons. That means mass number is same. So atoms of different elements having different atomic number and same mass number are called isobars. So isobars differ in atomic number, but they have same mass number. Examples. See here. Sulfur atomic mass is 40. Chlorine atomic mass is 40. This is one of the isotope of chlorine. Argon atomic mass is 40. Potassium atomic mass is 40. Calcium atomic mass is 40. I've shown here the examples. Argon 18 Ar40, potassium 19 K40, calcium 20 Ca40. So atomic numbers are different, so elements are different, but mass number is same. Mass number is same. Yes, and here it is being mentioned. So argon, it has got atomic number 18, mass number is 40, and number of neutrons is 40 minus 18 comes to 22. Similarly, potassium, atomic number is 19, mass number is 40, number of neutrons 40 minus 19 comes out to 21. Calcium, atomic number is 20, mass number is 40, and number of neutrons 40 minus 20 comes to 20. So only the mass number is same, atomic numbers are different. Yes. So these are called what? They are called isobars. They are called isobars. Example here. So you can see proper idea you will get. Argon, potassium, calcium. Atomic number of argon is 18. Potassium is 19. Calcium is 20. Mass number of all of the three is 40. How many electrons in argon? 18 protons means 18 electrons. Potassium, 19 protons, 19 electrons. Calcium, 20 protons, 20 electrons. And number of neutrons, just now we have calculated. For argon, it is 21. For 22. For potassium, it is 21. Calcium, it is 20. That is 40 minus 18, 40 minus 19, and 40 minus 20. Next one, isotones. What are isotones? Isotones are any of the two or more species of atoms. They are atoms or they are nuclei that have same number of neutrons. See, atomic for isotones, you know how we define isotones. Atomic number is different, mass number is different, but number of neutrons are same. Number of neutrons are same. You can see here oxygen, atomic number is 8, mass number is 16. Both are different, but number of neutrons, 16 minus 8 comes out to 8. Nitrogen, atomic number is 7, mass number is 15. This is one of the isotope of nitrogen. Okay, you can say mass number is 14. That is most abundant. Therefore, we take 14 only. Number of neutrons, 15 minus 7 is again 8. Carbon, atomic number is 6, mass number, one of the isotope of carbon, mass number is 14. Number of neutrons is 14 minus 6, that is equal to 8. So number of neutrons are same. Number of neutrons are same. And therefore, we say they are called as isotones. And these are few of the examples of isotones. You can see here, many examples are involved. Sulfur, 16, 36. 16 is the atomic number and 36 is the mass number. You can denote here mass number A, number of neutrons S, N. So 36 minus 16 comes to 20. Chlorine, 17 Cl37. Atomic number 17, mass number 37. 37 minus 17 comes out to 10. 18 argon, 38. 18 atomic number, 38 mass number. 38 minus 18 is number of neutrons, 20. 19 potassium, 39. 19 is the atomic number, 39 is the mass number. So 39 minus 19 comes out to 20 again. 20 Ca40. 20 is the atomic number of calcium, 40 is the mass number. It comes out to 40 minus 20 is, so N is nothing but A minus Z. It comes out to 20, right? So this is isotones. Like that, there are many such compounds, Yeah, we have one more, that is isoelectronic ions. Iso means what? We have seen now. We have seen examples of isotopes. Iso means same. Iso stands for similars of the same kind. So isotopes, atomic number is same, mass number is different. Isobars, atomic number is different, mass number is same. Isotones, both atomic number and mass numbers are different, but number of neutrons are same. Now, what are these isoelectronic ions? They are species. They may be atoms, they may be ions, containing same number of electrons. Containing same number of electrons. They are called isoelectronic ions. Now see, let me take the example. Na plus. Na plus has got how many electrons? To make this understand, Na has got how many electrons, you tell me? Na, atomic number of Na is 11, so it has got 11 electrons. Na plus means what? Plus means, please do remember, loss of electrons. And minus means gain of electrons. And the number denotes the number of electrons lost or gained. Na plus means loss of 1 electron. So 11 minus 1 becomes 10 electrons. Okay. Then F minus, fluorine, atomic number is 9. So fluorine has got how many electrons? 9 electrons. So 9 electrons, minus 1 means what? Plus 1, gain of 1 electron. Minus sign stands for gain. So it is again having 10 electrons. Then we have Mg plus 2. Okay. Magnesium, atomic number is 12. That means it is having 12 electrons. Plus means what? Loss. 2 means what? Loss of 2 electrons. So out of 12 electrons, 2 electrons are lost. So it becomes 10 electrons again. O2 minus. Okay. Oxygen, atomic number is 8. right? How many electrons? 8 electrons. So 8 electrons, minus means add of 2 electrons, gain of 2 electrons. How many? 2. So 8 plus 2 becomes 10. Similarly, aluminium plus 3. Aluminium atomic mass is 30, atomic number is 13. That means there are 13 electrons. So 13 plus 3 means what? Loss of 3 electrons. So it becomes 10 electrons. One more, nitrogen minus 3. Nitrogen has got 7 electrons, 7 atomic number. So it has 7 electrons. So 7 minus 3 means what? Gain of 3 electrons, it becomes 10. So look at all of them. Look at all of them. All of them have same number of electrons. Such ions, they are not having same atomic number, not having same mass number, not having same number of neutrons. These are ions. Even you can take neon here. They might be sometimes atoms. 10 electrons. This also comes. So they have what? Same number of electrons. And such species are called what? They are called isoelectronic species, which have got same number of electrons, containing same number of electrons. Yes. One more you have, isodiaphers. Isodiaphers are what? They are set of nuclides that have different number of protons, different number of neutrons, but there is same difference between protons and neutrons. Another very interesting part. Thorium atomic mass is 234. Uranium atomic mass is 238. They are considered as isodiaphers. Let us see how. The number of, so 238 is the mass number, okay? Fine. So number of neutrons in thorium. Okay. What is the atomic number of thorium? Atomic number of thorium is, atomic number of thorium is 90. Mass number of thorium is 234 given. Similarly, so I'll calculate neutrons. 234 minus 90. Okay. Similarly, for uranium, atomic number is 92. Mass number is 238. What is number of neutrons? 238 minus 90. In both the cases, the difference between the neutrons and protons difference you want, okay? Not difference between number of neutrons, I'm not speaking. Understanding? Okay. Here, how many number of neutrons are there? 234 minus 90 comes out to 144. This is number of neutrons in, we'll take it here better way. Okay, we'll consider this. Thorium and here uranium. Atomic number of thorium is 90. Mass number given is 234. Atomic number of uranium is 92. Mass number given is 238. So number of neutrons, 234 minus 90 is 144. And here number of neutrons, 238 minus 92. 238 minus 92 comes out to 146. Okay. This is number of neutrons. Now difference between number of neutrons and protons. So N minus P is what? 144 minus 90. How much you get? 90. We get 54. And here also difference between number of neutrons and protons, N minus P. Here N is 146 minus 92. How much we get? 54. See, the difference between protons and neutrons is same. in these two atoms. So these two atoms are called isodiaphers. They are called isodiaphers. Understood? So they are called isodiaphers. So this is what we call it as isodiaphers, and the same example I have concluded here. So difference between protons and neutrons in both the cases will come to 54. You can check it out. I have explained it. So they are called isodiaphers. Yes. Okay. So with this, we are going to discuss further atomic mysteries. So we'll have to understand this further atomic mysteries, we need to understand the nature of electromagnetic radiations and the study of Maxwell's electromagnetic theory. Before that, what were the developments which led to the Bohr's model of an atom? Why Bohr's model of the atom came into consideration? One was the drawback of explanation which was given by Rutherford. Next, there were two main developments which played a major role in the formation of or formulation of Bohr's model of an atom. Which were those two? Dual character of electromagnetic radiations, which means that the radiations, they possess both wave-like properties and well as particle-like properties. And second was experimental results regarding atomic spectra, which can be explained only by assuming quantized electronic energy levels in an atom. We'll understand both of them in the further slides of our study. Okay, let us first understand what is electromagnetic radiation. So what are electromagnetic radiations? Electromagnetic radiation, students, they are nothing but waves. What are electromagnetic radiations? They are nothing but electromagnetic waves, you can say. We abbreviate it as EMW, or sometimes we write EM waves. Okay, they are waves. So when I say they are waves, how are these waves formed? When I hit water, the waves of water are formed. Similarly, when I hit a string, holding a string tightly at one side, the waves of string are formed, right? Similarly, what are these electromagnetic radiations? If they are waves of what? So electromagnetic radiations are the waves which are formed as the result of oscillating electric and magnetic fields. So when there is a wave, we say this is a wave, it has oscillating electric field and magnetic field. Then how are those fields? The oscillating electric and magnetic fields are perpendicular to each other. They are perpendicular to each other. So if I say this is electric field, can you see this white line? White part is electric field. Then this part is magnetic field. You can see here, both are perpendicular to each other. Both are perpendicular to each other. Yes. So I call this as electromagnetic wave, and this is the direction of propagation. Yes. So electric field, direction of propagation, and magnetic field. You can see all of them are at an angle of 90 degrees. They are at an angle of 90 degrees. Understanding? Imagine it in a three-dimensional view. So electromagnetic radiations are those which have electric and magnetic fields which are perpendicular to each other and also to the direction of propagation. So all of them perpendicular to each other. If this is direction of propagation, this is electric field and this will be magnetic field. So all of them make an angle of 90 degrees. They make an angle of 90 degrees. Yes, electromagnetic radiations is a radiant energy that includes different waves. Radio waves are there, microwaves are there, visible light is there. We come across only visible light. That is only falling under our wavelength of vision. X-rays, gamma rays, they differ in frequencies and wavelengths. To understand these concepts more clearly, let us try to understand the characteristics of these waves. What are the characteristics of these waves? What all comes under this? So see, you can see here. So we have radio waves, microwaves, infrared rays, ultra visible light, ultraviolet, VIBGYOR, what you study, violet, indigo, blue, green, yellow, orange, red. Yeah. Then we have ultraviolet rays, X-rays, gamma rays. Here you can see this is of low frequency. This is of high frequency. High frequency, shorter wavelength, low frequency, longer wavelength. Let us see one by one what are they. Then we'll come to this again. So what are the properties of electromagnetic radiations? So the first one, they can travel through empty space. What does that mean? They do not require any medium and can move in vacuum, unlike sound waves. Sound waves, if you see, they need some medium to travel. They cannot be propagated in vacuum. If you are present in a vacuum, you will not hear anything. Understanding? But these electromagnetic radiations, they can travel through empty space. That means they can even travel through vacuum. Waves other than electromagnetic waves have to travel through some medium, some substance. For example, sound waves need either solid, liquid, or gas to pass through. Yes? Okay. The speed of light, which is 2.9979245 into 10 into 10 raised to 8 meters per second, that is 3 into 10 raised to 8 meters per second, is always a constant. Yes, its value is the speed of light. It is denoted by symbol C. It is 3 into 10 raised to 8 meters per second, and it is always a constant. Okay. Wavelength is commonly characterized by the symbol lambda. This symbol stands for lambda. It is the measure between the distance of either troughs or crests. Let us see what is wavelength and all. Yeah, what is crest, what is a trough and all. Okay. Okay. The nature of electromagnetic radiations, electromagnetic wave theory. This theory was being put forward by James Clerk Maxwell in 1864. The main points of this theory are as follows. See, whatever I'm now talking about, I'm talking about the electromagnetic waves. I'm talking about these waves. Yes. What are electromagnetic waves? They have electric and magnetic fields. By nature only, they have electric and magnetic field, students. Nobody has created them. By nature, all these radiations come from sun only. So these, therefore, they are called electromagnetic radiations. They are waves which contain electric and magnetic fields. How they are present? They are present in perpendicular nature at an angle of 90 degrees. Not only electric and magnetic fields, but also the direction of propagation, in which direction it is propagating. And these are all the examples for electromagnetic radiations, right? Not examples, they are the characteristics of electromagnetic radiations. I'll come back to this slide once again. Properties of electromagnetic, so nature. The energy is emitted from any source. You can consider any source continuously in the form of radiations, and that is called radiant energy. From any source you take, energy is emitted continuously in the form of radiations, and it is called radiant energy. So these radiations consist of what? They consist of electric and magnetic fields oscillating perpendicular to each other, and both are perpendicular to the direction of propagation. I hope you are getting this point of mine. Yeah. So let me say there is some source here and the ray is moving. A wave is moving in this direction. Yes. So this is direction of propagation. So this is called what? Direction of propagation. Propagation. Okay. So it will move in the form of wave. So it will have electric field, say like this. So is it not perpendicular to the direction of propagation? Yes. And it will have magnetic field like this. Imagine it in the form of three-dimensional space. Then you'll understand it. The one which I had shown previously. Yes, the one which I had shown previously. That is nothing but the same. Correct? So it will have electric and magnetic fields which are perpendicular to each other and perpendicular to the direction of propagation of the radiation. The radiations possess wave character and travel with the velocity of light 3 into 10 raised to 8. So 3 into 10 raised to 8 meters per second. So this is the velocity of light. These waves do not require any material medium for propagation. That means they can even travel through vacuum. They can even travel through vacuum. For example, the rays from the sun reach us through the space, which is a non-material medium. So in space, there is purely vacuum, right? So the rays of sun travel from our atmosphere has got a medium of air. But what about the space? There is nothing available there. It is completely vacuum. Still, the rays of sun pass from that and reach the earth, right? So therefore, we say the electromagnetic radiations do not require any medium for propagation. They can travel even in vacuum. Characteristics of a wave. What are the characteristics of the wave? First one, wavelength, denoted by the symbol lambda. Lambda. It is defined as the distance between any two consecutive crests or troughs represented by x. Yes? Okay. So what do we mean by a crest and a trough? See, when you have a wave, yes, the wave moves like this, correct? The upper curve is called, this is the direction of propagation. This is origin. The upper curve is called crest. All upper curves are called crests. And the lower curve is called trough. The distance between two successive crests. So this is the two successive crests. This distance is called wavelength. This distance is called wavelength, denoted by the symbol lambda. Denoted by the symbol lambda. And its SI unit is meter, because wavelength, it is length, right? It is meter. But usually we measure it in angstrom or nanometer. Angstrom, STROM, denoted as A naught. 1 angstrom is equal to 10 raised to minus 10 meters. And we also measure it in nanometers. 1 nanometer is equal to 10 raised to minus 9 meters. SI unit is meter, but usually wavelength is measured in angstrom and nanometers. Next one, frequency, denoted by F, or we denote it by nu. Frequency of a wave is defined as the number of waves passing through a point in 1 second. It is denoted by the symbol nu. Nu, yes, it is denoted by the symbol nu. It is pronounced as nu, and it is expressed in hertz. Hertz is the SI unit for frequency. So what do we mean by frequency? Number of waves passing through a point in 1 second. This is a point. So let me say, if I have a point till here, so how many waves? This becomes one cycle. This becomes a second cycle. This becomes third cycle. Like that, how many waves, how many cycles are being completed in 1 second? That is frequency. Yes. How are wavelengths and frequencies interrelated now? How they are interrelated? I'll make a simple thing to make you all understand. See, let me say I have a wave here. So up to this point, I'll consider I have a wave like this. So here, wavelength is this, correct? So here I can say wavelength is more, right? How many waves? 1, 2. So there are 3 waves. So frequency is 3. One more I will consider. I'll consider till same point. Imagine that this is same length, okay? And here I will have the wave like this. This is also a wave, right? Okay. Okay. So what is wavelength here? Look at this. Wavelength is this, lambda. So wavelength is what? Less. Frequency, calculate same point. Okay, same point. Imagine this is same point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 frequency. Frequency is 10 cycles. Understanding? So as wavelength increases, frequency decreases. Or as wavelength decreases, frequency increases. So how are they related to each other? They are reciprocal of each other. Or I can write it like this also. Wavelength is reciprocal of frequency. As wavelength increases, frequency decreases. And how energy is related? If the frequency is more, energy is more, right? If frequency is more, energy is more. So can I say they are directly proportional? So as frequency increases, energy also increases. As frequency decreases, energy also decreases. Yes? Then how it is related to wavelength? As wavelength increases, frequency decreases and therefore energy also decreases. As wavelength decreases, frequency increases and therefore energy also increases. Please do remember, frequency is directly proportional to energy and inversely proportional to wavelength. Correct? So these are the relations which we should be knowing. And there are many more relations also we'll come across. Okay? Velocity. Velocity of a wave is defined as linear distance traveled by the wave in 1 second. It is represented as c and expressed in centimeters per second or meters per second. Usually we take meters per second. Amplitude. Amplitude of the wave is the height of the crest or depth of the trough. It is represented by symbol A. Actually, amplitude is represented by the symbol A, capital A, not P. and is expressed in units of length, amplitude. Yes, height of the crest. Here you can see height of the crest. This is amplitude, or depth of the trough. It is amplitude. Wave number. Wave number is denoted by the symbol nu bar. It is defined as number of waves present in 1 meter length. In 1 second, it is wave number. It is frequency. So what is frequency? Cycles per second. In 1 second, how many cycles? How many waves? That is frequency. What is wave number? Cycles per length, per meter. In 1 meter, how many cycles? Yes. So wave number is also inversely proportional to wavelength. Wavelength, lambda. As wave number increases, as wavelength increases, wave number decreases in 1 meter. Understanding? So it is denoted as nu bar. Nu bar. Next, time period. The time taken by a wave to complete one vibration is called time period. Time taken, so SI unit is seconds. It is seconds, and you can see here. So this is direction of propagation. This is crest, and these are troughs. Here we have wavelength, successive crests or successive troughs. This is amplitude. So I can show here. This is crest, crest. This is also crest. Upper curve is crest, downward curve is trough. Distance between the two crests is wavelength, and one cycle, this is wave cycle, and time required, this is time period. Height of the crest, height of the crest or depth of the trough is amplitude. Yes, it is amplitude. So here with this, we understand the different terminologies. So how are related? So C is what? Speed of light, that is velocity. Nu, frequency. Lambda is wavelength. So C is equal to nu into lambda, that is speed of light is equal to frequency into wavelength. Yes, and W, that is wave number. Wave number is denoted by the symbol nu bar is equal to 1 by lambda. And even frequency, nu is directly proportional to 1 by lambda. Remove the proportionality sign, mu is equal to C by lambda we get. And what is C? It is lambda into nu. That's it. Understood? So these are different relations between the characteristics of different waves. Characteristics of different waves. Okay? So these are the relations. Next, what we come across is, we come across the electromagnetic spectrum. Okay, I'll discuss this part now. Here you will understand. You can see here now. Okay? So what we understand here, the different electromagnetic radiations starts from radio waves. Starting from radio waves. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. These are, and visible light over here. Okay. If you observe here, the wave is shown like this. So this is the waves of radio waves, then comes microwaves, then comes infrared, then comes visible light, which can be recognized by our eyes. Then comes ultraviolet, X-rays, gamma rays. Okay. Infrared is divided into three. Far infrared, far IR, middle IR, and here we write near IR. The infrared region, which is near to the visible light, we call it as near IR. In the middle one, we call it as middle IR, and which is away from the visible light, we call it as far IR. Okay. Then, so what does this indicate? Radio waves, they have got very long wavelengths. So radio waves have long wavelengths. Long wavelengths. So when wavelength is long, we know that lambda is inversely proportional to frequency. So they will have how frequency? They will have very low frequency. So only when you might have seen your elders using radios, right? Radios, the stations of radios are not very clear. Why they are, I'm sorry, I wrote the wrong thing. It is not wavelengths. It is low frequency. why the stations of radio waves are not so clear? Because the frequency is low. Why the frequency is low? Because the wavelengths of these radio waves, these electromagnetic radiations, are very long. See, they are very long. Therefore, what happens? It has got low energy. Therefore, the stations are not very clear. Then after that comes microwaves. A bit less longer wavelengths they have. So frequency will be slightly more. Yes. Then we have infrared rays. The frequency slightly increases. As you move from radio waves to microwaves, then to infrared, the frequency increases. As frequency increases, what we say? We say there is decrease in the wavelength. Yes, there is a decrease in the wavelength. Yes or no? So there will be decrease in the wavelength. Then comes visible light. Then comes what? Visible light. So we say there are 7 types of electromagnetic radiations. In that, visible light makes us all the things visible to us. Yes, visible light. So how do we explain regarding visible light? You can see there visible light, usually we say it is VIBGYOR. So how do you define visible light? It is a form of electromagnetic radiations, visible light, that are visible to most of the human eyes. Yes. So what is the spectrum? What broad range by wavelength of the broad range of wavelength is known as electromagnetic spectrum. This particular range is known as electromagnetic spectrum, which is visible. It consists of 7 colors: violet, indigo, blue, green, yellow, orange, and red, which you term it as VIBGYOR. Yes or no? VIBGYOR. Yes, which is termed as VIBGYOR. Correct. So you can see VIBGYOR. When you have violet, this side is violet. That means frequency is more. Frequency is more. Correct. And here we have less frequency. Or sometimes this is given in hertz, and here frequency wavelength is given in nanometers. So what is the nanometer range for human eye? Human eye can detect. Human eye detects wavelength from 380 nanometer to 700 nanometer. 380 nanometer to 700 nanometer, and in that range only our visible light falls. Our visible light falls in that range only. Therefore, we are able to see the visible, we are able to see the objects. We are able to see the objects. Understanding? So here, VIBGYOR is there. Violet falls under larger frequencies and red falls under lower frequency, or I can say red falls under long wavelength and low frequency only when I'm speaking about visible light, and violet falls under short wavelength, or you can say high frequency. High frequency. Correct. So visible light is a form of electromagnetic radiation. These waves are occurring as colors of the rainbows, where each color includes what? Different wavelength. Each color shows different wavelength. Red has the longest wavelength. Red has, in VIBGYOR I'm speaking, okay. When you compare all the electromagnetic radiations, radio waves has the longest wavelength. But when I speak about visible light, red has the longest wavelength, and violet has the shortest wavelength. Shortest wavelength. When all the waves are seen together, when you see all the wavelengths together, it appears in the form of white light. See how beautiful the nature is. Yes, when all the waves are seen together, they form white light. And when this white light, when the same white light you pass it through the glass prism, again this light breaks into 7 colors. And those 7 colors are nothing but your VIBGYOR: violet, indigo, blue, green, yellow, orange, and red. Yes, it appears in the form of VIBGYOR. It appears in the form of VIBGYOR. Correct? So violet, indigo, blue, green, yellow, orange, and red. So electromagnetic radiations, they can be transmitted in the form of waves or particles at different frequencies and wavelengths. And this wide range of wavelengths is known as what? It is known as electromagnetic spectrum. It is known as electromagnetic spectrum. Yes. So you may say, what is visible light spectrum then? The portion of this entire electromagnetic spectrum that is visible to human eye. So this is visible electromagnetic spectrum. What I'm saying here is, when you take all the wavelengths and put it under certain, you stand for a group photo, right? All the people, they stand in a line for a group photo. That is called photograph. Similarly, when all the waves are clubbed together, it forms all the electromagnetic waves. When they are captured in one photographic plate, we call it as electromagnetic spectrum. We call it as electromagnetic spectrum. And that electromagnetic spectrum which is visible, we call it as visible electromagnetic spectrum. So visible light range comes under range of electromagnetic spectrum between infrared and ultraviolet. Frequency 4 into 10 raised to 14 hertz, 7 into 10 raised to 14 hertz. Sometimes we write 8 into 10 raised to 14 hertz. Color, you can observe here. The most important characteristic of visible light is what? It is color, which is both inherent property of light and an artifact of the human eye. Yes, our eyes include specialized cells known as cones. These cones, they act as receivers. Understanding? So eyes, because of those cones present in the eyes, they receive these colors and we can identify the colors. Okay, so this is about visible light. So longest wavelength in visible light is for red. Shortest wavelength is for violet. Highest frequency is for violet. Lowest frequency is for red. After this visible light comes what? Ultraviolet radiations. So ultraviolet radiations are the radiations which fall after visible light, and they have more frequency, high frequency than visible light. Yes, so only we say our earth is protected by the protective layer of ozone, which prevents us from harmful ultraviolet radiations. After visible light, what all radiations come, electromagnetic radiations come, they are all harmful radiations. Ultraviolet radiations might be X-rays, might be gamma rays. They have the penetration power. Yes, ultraviolet radiations are found to cause different skin diseases. X-rays penetrate through our body. Gamma rays are still more, they have still high penetrating power. Why is this? Because the ultraviolet rays, X-rays and gamma rays, they have high frequencies. They have got very high frequencies, and therefore the penetration power is more. Now you can see here, 10 raised to 16 hertz. That means 10 raised to 16 cycles in 1 second. 10 raised to 18 hertz, 10 raised to 18 cycles in 1 second. So the frequency goes on increasing, therefore the wavelength goes on decreasing. So X-rays, gamma rays, they have got short wavelengths and therefore high frequency. So let me conclude with some of the questions now for y'all. So see here, which out of electromagnetic radiations, the radiations with longest wavelength is what? Radio waves. Right? The radiations with shortest wavelength is gamma rays. Gamma rays. Denoted like this also, gamma rays. Then the radiations with highest frequency I can say, or I can say highest energy also. It is which rays? Gamma rays. With lowest frequency or lowest energy is what? Radio waves. This is for entire electromagnetic waves. Now my question is, invisible light. Invisible light. The radiation, which color? Visible light is nothing but VIBGYOR, VIBGYOR. So invisible light, which has longest wavelength? Which has longest wavelength? So longest wavelength is for red. And which has shortest wavelength? Shortest wavelength is for violet. The other way around, which has high frequency? High frequency. It is again for violet because it is having shortest wavelength. Which has got low frequency? It is red. Yes, and this entire band of different wavelengths, when you arrange all these electromagnetic radiations in the form, either considering the wavelengths, range of wavelengths, or considering the range of frequencies, what is that called? It is called electromagnetic spectrum. Electromagnetic spectrum. When I'm talking only about visible light, I call it as visible electromagnetic spectrum. Only this is visible to our naked eyes. When you see all the colors together, when they come together, we see the light as white light. And when the same white light is passed through a prism, yes, it divides, it disperses into again 7 colors. That is our VIBGYOR. Yes, this is called dispersion of white light, right? Dispersion of white light. So this is about our electromagnetic radiations. Yes, and we have seen the properties of electromagnetic radiations, all the characteristics and the relations which are very important also we have seen. Wavelength is inversely proportional to frequency. Remove the proportionality sign, C by nu. Therefore, what is C? Nu into lambda. Yes. Wavelength is also inversely proportional to energy. Yes. But frequency is directly proportional to energy. Therefore, I can say wavelength is inversely proportional to energy, which is also inversely proportional to frequency. Wave number. Yes, we denote it like this. How do we write wave number? This is not denoted like this. Wave number, nu bar, is inversely proportional to wavelength. You cannot write C by lambda. This is C by lambda. Frequency is C by lambda. Wave number is 1 by lambda. Yes, as wavelength increases, the wave number decreases. Okay, so using all these, we can come to certain different conclusions also. So C is equal to nu into lambda. Lambda, but I know that lambda is equal to 1 by nu bar. So can I write C is equal to nu into 1 by nu bar. So C is equal to what? Nu divided by nu bar. Yes, this is another relation. So all these relations will help us for solving the numericals. Yes. So with this, I complete the explanation of this electromagnetic radiations here today. In the next video, we'll be going with further part of the chapter. Hope you have understood. Thank you.